All right, thanks everyone for joining. It's really a great honor for me to be here, and I'm very excited to share our recent work on developing terrain-aware high-mobility robots towards future planetary explorations. So robot-aided exploration has already been an essential tool for our planetary missions. We rely on our robots and rovers to gather invaluable data and make scientific discoveries, which otherwise would be out of our reach. And now, more than ever, as we are preparing to go back to the moon and eventually land in Mars, the expectation for these robot-aided missions are higher than ever. And it's a great opportunity, but also the stakes are really high, because to succeed in these planetary surfaces, our robots not only have to reach safely in these destinations, but also have to be reliably operate across a diverse range of planetary surfaces, and also to adapt their operation flexibly based on the changing environmental conditions. And that is certainly not an easy task, because planetary surfaces are among the worst and most complicated environments that our robots must traverse and operate in. There are, for example, on Mars, there are large scattered rocks and boulders, there are steep craters, all posing significant challenges to our wheeled rovers or other form of exploration robots. And just to make things worse, most of these surfaces are also covered in unconsolidated, loose regolith that can deform and yield and flow, and causing our robots to slip, to sink, or getting completely stuck, which can cause us great cost, which means that whenever the robot gets stranded on Mars, such as one of the rovers previously, it cuts off our opportunity to continue to make great scientific discoveries. And these challenges extend well beyond locomotion and navigation, and extend into excavation, sampling, and other operation schemes. So to address some of these challenges, my group is very interested in developing new sensing and locomotion and planning tools to enable robots to have a better understanding of their physical environments, and to select exploration actions that are tailored to the physical property of their environment. So in today's talk, I'm going to focus on 3 key questions that we seek to answer. The first one is, how can robots gather or effectively gather information about their environment, especially extracting physical properties of their environment through interactions? And specifically, I will talk about how we can turn robots into scientific instrumentations and use their legs to gather information about the environment through every single step they take. The second part, I'm going to focus on some of the locomotion tools and models that we're developing, which allows the robot to predict the outcomes of their interaction with this environment based on the sensed properties, and then make decisions about their exploration, either individually or cooperatively within a group. And combining both, I'm going to show you examples from our recent field work and testing in analog environment to show how these tools and new methods, capabilities can start to enable robots to better collaborate with each other and adapt their exploration to enable better science. So let me start from the first challenge. So when you drop off a robot in an unknown environment on the space that you have never been, one of the biggest challenges is how to gather information about the environment as we go, such that we can make decisions based upon these understandings of our physical environment. And specifically, one of the challenges that my group focuses on is regolith mechanics and properties. So we know that many of these unconsolidated materials and regoliths on the moon and the Mars and other planets can cause significant challenges for a variety of operations, as we mentioned, including mobility, navigation, drilling, excavation, and construction. It's very important for us to be able to assess the property of our environment before we send a rover to navigate through, so that it doesn't get stuck in a sandpit, or before we make decisions about where to construct habitat on a planetary surface. However, the challenge is that these properties, such as how soft and how much strength the regoliths are on the moon or on the Mars, can be quite difficult to discern by vision alone. So as I'm showing in the example here, even just the same composition through different compaction, the sand that's loosely packed and closely packed can look quite similar through the naked eye, but they can differ in strength by more than 5-folds, even with a couple % of different packing fraction. And that can be life and death difference to our rovers navigating on top of them or for construction tasks that needs to be on top of these regoliths. So for us humans and many of the animals, when we are walking, our feet is providing information that sometimes can be more informative than vision. So when we are walking on the beach, our feet tells us every step whether the sand is soft or compact or wet. And on top of that, we can even feel maybe are there any ice that's crunchy, are there any snow? So these signals are actually super informative when we are exploring or sending a rover to the outer planet, because one, this information is for free and they're really dense. Every step, if we can gather this information and parse them, we get really high spatial density of information that we don't have to stop and measure. And two is that while we are doing that, we can parse out this information to aid with operation while executing other tasks. So as the robot are, for example, transporting material, they can collect information for free opportunistically. So one of the ways that we are doing this is we want to not rely on any extra sensors, because more moving parts is more possibility for failure. So our choice of approach is to use proprioception-based sensing. So I'm going to show you a video of a spinning direct drive motor, and a human in the video is going to blow air onto the motor. The motor has very high force transparency. It can feel that puff of air and then switch their rotation direction. So because of this high force transparency, if we make robot legs using these actuators, you can imagine that the leg can be super sensitive to any external forces the leg felt. And that can build us robots that can sensibly feel the world from every single interaction. However, why haven't we come up with the idea sooner to use these to build robot legs that can map the world for them? Well, gearboxes exist for a reason. So until very recently, direct drive motors, despite their high force transparency, have very limited power density. Until very recently, it has been figured out that increased gap radius could enable and significantly improve torque density, and then we get to use them in leg mobility. So this provides us with a great opportunity to start to use a new way of building robot legs and having them serve as not only locomotive limbs, but also as sensors or even scientific instrumentation to characterize regolith mechanics in these planetary explorations. So that's the starting point when we start to explore the possibility of using robots as sensors. But since our goal is not to only detect contact, but to precisely characterize the scientific mechanics of the regoliths, use them as instrumentation, we did not immediately start from these two amazing quadrupedal robots, which is Minotaur and Spirit, which has very low gear ratio actuators. Instead, we started with one leg out of the Minotaur robot. And this is work by my amazing undergrad student, John Bush, when he started his freshman year with me. So John he built a single leg mounted on a static stand using direct drive actuators that has a very high force transparency. And he named it after the well-loved USC mascot, Traveler. So Traveler is a 5-bar linkage leg, has two coaxial motors that drive the two upper linkage of the leg. I'll show you a video in a second. And these motors can send the toe to different positions, performing a diverse range of sensing protocol, poking or scraping on the regolith. And also, since it's direct drive, it has high force sensing capability. When the force is applied to the toe from the regolith, by sensing the motor current or the motor torque at the joint, through the kinematics, we can back out how much of the force is applied. So John made a couple of different configurations of the leg for us to start our lab and field testing and validation. One of them we mounted on a static ergonomic test stand that our collaborators in planetary scientists or earth scientists can easily carry them to the snow mountain or to the desert or the hill slope to perform these geotechnical and planetary tests. And then the other one is we set up a mounting scheme for them to mount on other robots and rovers, such that we can initially decouple locomotion and sensing to gather rich data to validate the capability. So here is a video showing the robot performing a very simple sensing protocol. Following the green arrow, the toe lowers a couple of centimeters into the soil, and then following the blue arrow, the toe drags horizontally through the soil. And on the bottom plot, I'm showing you the inferred force in the X, which is the horizontal direction, and also the Y in the vertical direction. What you can see is during the green shaded region, as the leg vertically penetrated into the soil, the force Fy here, which is the vertical normal force, increased almost linearly and rapidly with the penetration depth. And the rate of that increase is going to determine how soft the stiffness of the soil. And then at the blue shaded region, the leg scrapes through the soil, we can measure the shear strength. And even these two very basic sensing protocols can already reveal a lot of rich signals about the material's strength. But I'll show you also later that we can developing active sensing protocols that can, based on the hypothesis, to inform different actions for the robot to gather information of the environment. So the first thing that we want to understand is how accurate is this force sensing capability before we deploy it in our field experiment. So in order to test that, we used a lab experiment using a fluidized bed. So for those of you who have not seen a fluidized bed, it has a giant blower connect the air that can blow into the air chamber. And then we have it flow through a porous plastic to fluidize the sand or any of the planetary simulant you can put inside of the test bed. What happens there is when you crank up the airflow, the larger airflow you send, the softer the sand becomes. So that was one poor crab that thrown into the fluidized bed back in the days. It was the first time the crab ever see a fluidized bed and why the world is crumbling around it. So it looks a little bit confused, but later on we actually run locomotion experiments with the crab and it adapts actually really well. But this is how the fluidized bed works. And by controlling the airflow, we can easily control the strength of the sand or any of the regolith simulant. And in addition to that, after any of the surface disturbances, we can quickly just send the airflow to fluidize the sand and then erase any footprint or erase any interaction to reset the ground to make sure that we have a consistent initial condition. So the test we do is we mount the direct drive robotic leg on top of fluidized bed. And once we set the fluidized bed to different sense strengths, we poke the leg into it, and then we measure the force responses. So here is the one of the results that we get through these lab experiments. So the curve from the top to bottom is when we set the sand strength or the volume fraction, which is the packing density of sand, from the highest to the lowest. On the x-axis, you have the depth measured from the surface to the toe position. On the y-axis, you have the resistive force in the normal direction from the surface. So as you can see, the slope, which is sort of the stiffness of the sand, decreases almost linearly as you reduce the volume fraction, which is very consistent with our previous lab-grade measurement and also granular literature. So this verifies that our lab can actually measure accurately the surface property in the strength size. But we're not even satisfied with that. We want to see what other texture or layering or other rich signatures the leg can detect. So once we validate the basic accuracy of the leg in lab experiment, we brought the leg to deploy in two different field sites. One is Y-Sense in New Mexico, which is a dune field that possesses very similar features, such as the sand ripples and the crusty surfaces that has been observed by the Opportunity rover on the Mars. The other one is at Mount Hood in Oregon. Aside from it's a really nice ski field, which I highly recommend if you have not been, it's also a very unique site with glacier and volcanic dust. So it forms this very unique icy regolith mixture that's actually very similar to what we would be interested in the permanent shadowed region of the moon as we return to understand those icy regolith mixture. This is part of our NASA P-STAR project called LASSI, where we have an amazing team with planetary scientists. Many of them serve on the Mars rover science team, who cares about understanding the involvement of the moon and the Mars. We also have roboticists, of course, working on the team to develop new technology to facilitate these planetary science. And in addition, we have decision scientists studying the human-robot interaction and also the human decision-making model to understand how science team make decisions and adapt their experiment plan based on the information brought by the robot. So here is some of the results we have gathered from our field site. The first field trip that we went to is at Mount Hood. So again, the Mount Hood has a rich form of icy regolith with different ice content, with different binding form between the ice and the grains. And this is one of the first pokes when we send the lag into the soil. I'm going to show you a video here. So you can see as it penetrates through the surface ice cap, there's a sudden force drop, and then later on there's a ductile drop. Let me play the video again. That's one failure, and the second ductile failure. You can see that these actually these actually possess very different failure signature. So very different from the homogeneous material that we were showing from the lab test, where as you poke deeper into the sand, the force just uniformly, linearly increase with depth. Right now, when the surface ice rupture, you have very sudden failure signature and large drop in force. And later, when you penetrate into the more cohesive soil that has small ice frozen bridges in them, you have this mellow, extended plastic failure range. So the first peak error is from something like this, right? We have high ice content, almost like glass sheet that ruptures under the load. And the second one is more interesting because you have mostly dominated by this cohesiveness of the ice grain mixture. So one of the interesting things about this rich signature is that by looking at the force responses, we can now infer what type of icy regolith form it is, and then what might be the ice content. That can be super interesting for our lunar exploration because there are a lot of interesting hypotheses about how does the water get to the moon, how was it preserved over time. That represents and help us understand the past and present of the environment. And then by looking at these force responses, if we can figure out the potential form of these ice grain bindings and the ice content, they can help us test some of these delivery mechanisms in the future. So we're very excited about this perspective. And similarly, from our Y-sense, which is the Mars analog, we also had very exciting findings. So one thing that we are interested in is looking for life, right, in Mars or other planets. And specifically, we want to look for either past or present bioactivities. And turns out we can also gather that information, further information through force. What I mean by that is Y-sense is a very interesting environment. So it has a year-long consistent wind blowing direction, and the dunes start to stabilize towards the direction that wind blows. If you look at the left side image, it's showing an upwind sand dune that's mostly arid. There's no vegetation, right? The dune is still actively migrating. The second image, the parabolics, is more stabilized dune where vegetation starts to grow. You have significantly increased bioactivity in those sites. So both sides have very similar crusty surfaces on them. But when you poke at them, the force signature of the crust is significantly different. So I'm showing you the first video is at the Barken side, the arid side, with very minimal activity. You can see that it's very similar to the ice cap failure signature, where as the leg poke into the surface crust, it has a suddenly brittle break. However, if you look at the parabolic one, also surface crust, but the failure is much more ductile. It's more leathery as you poke in and elastic. So we were actually wondering for the longest time why that difference was looking like this. We actually have a lot of data because every poke we gather is for signature, and they distinctively show up in both signature, in both environment. And then until our collaborator in planetary science, Natalie Jones, she had a very cool hypothesis. So she studies a biopolymer called EPS for the longest time. Oh, sorry. And, sorry, I forgot to mute the video. You can see the wind is blowing in there. So you can see that the EPS is actually this biopolymer emitted by the bacteria activity. And even though those bacteria has already died off, they left behind these polymers inside of the crust. You can see these little strings that pulls the grain together and forming these cohesive bonds. So that is basically causing the ductile responses from the site where we see those increased bioactivity site. In fact, when we actually look at the correlation between the force drop, the brittleness with the EPS content, we see a very clear trend there. So the implication of that is by looking at these force responses and the resilience of the crust signature, we can potentially reveal signs of either past or present bioactivity on different planets. And that's also another very interesting perspective for how to use these force sensors, force sensing method to aid with planetary science discoveries. So now that we're very excited about potentially through force to understand all these rich understanding of their planetary environment, one thing we need to do is we need the legs to walk themselves so that we can gather information through every single step and form a rich data set. So one of the key things is we need to figure out how to have the robot walk in either dynamically or starting slow and eventually dynamically while still maintaining this high precision force sensing measurements. So we started to make this sensing capability into our quadrupedal robot here, the Spirit robot. A Spirit robot has low gear ratio joint. As we were showing you, it's not direct drive, but it's very low gear ratio 6:1. So the actuators still have very high force sensing accuracy, but also gives a little bit more torque density for supporting, preventing the motor from overheating during extended leg mobility. It also have differential GPS to record the trajectory of the robot path in these field adventures. So the first thing that we did is we started to develop a sensing gate for the robot to walk while still maintaining the sensing accuracy. So we started with relatively slow and static gates. This is work led by my postdoc Diego and my another amazing undergrad Ethan. So they started by looking at a gate where the robot always support its body using 3 legs and move 1 leg at a time. So this is the most similar we can get to the static field test stand we mount the leg at, because this prevents a lot of the inertia, prevents the body pitch, roll, and yaw. So we can relate the force responses and identify the segment that relates to our force measurement. So we run the robot through this track where we replace the center block to be different compaction of sand or with sand with surface crust. And we look at the strength at the force per unit, so how quickly the force increase with steps, similar to what we show you in the lab settings. So here is the initial results from the lab trial. So the bar graphs are showing the sense stiffness measurement from every single step from all 4 legs, because for a quadrupedal robot, each of its individual leg can serve as a sensor through every step. And the shaded area is the steps when the robot walks into the sand, when that particular leg steps into the sand. So you can see that actually the robot can quite effectively distinguish the sand region where it steps into the soft material. But of course, the more exciting things happens when we deploy the robot in these planetary analog field sites. Again, we went back to the Y-Sense and Mount Hood, where we start to measure the robot force measurement through during the locomotion for the spatial regolith properties. And this is one of our initial tests, where we run the robot from more packed sand to a loose sand region, while every step we record the toe position, the toe force, and then through the force versus steps recording, we can compute the stiffness of the sand. And you can see that from the packed sand region to the loose sand region, the estimated normal strength from the robot leg decreased significantly. The other interesting is that if you look at the force per depth curve, you can clearly see that in some of regions, there is a little decreased force drop, the indication of the surface crust. So our current work is characterizing the accuracy of the surface crust detection as well as the strength detection against ground truth. The other interesting deployment that we did is at this Mount Hood, which is a very patchy environment with different patches of ice-soil mixture with different ice content. So due to the patchiness of the environment, it's crucial that we produce a very high spatial resolution map of the regolith strengths because things can vary quite quickly over short distances. So the top diagram is showing our science team before sending the robot, looking at the boundaries visually and determining what are the scientific targets and where should the robot work. And the bottom video shows one of the GoPro cameras we mounted on the robot, recording every step it takes, along with force sensing data. So we use the force sensing data from every step, which is the circular markers on both plots. And on the bottom plot, we are using the Gaussian process to infer the surface property through the every step measurements. And you can see that when the robot is working on the path one from the snowfield to the low ice content dirt to snow again, the strength variation over short distance can be well picked up by the robot strength on the bottom plot. So this is very promising. And now that with the capability for the robot to create this regolith map, our vision is to, one, use the robot as a scout in front of rovers to identify potential scientific valuable sites, such as the site that may contain water ice or contain interesting crusty signature that of scientific value. But at the same time, by zigzagging through or scouting through certain paths, have the robot to identify the traversal risk for the rover. So we want the robot to, since the leg robot, this leg dog is much less expensive as compared to the wheeled rovers, we wanted to basically map out the terrain and identify where the soft sand pit is, such that we can have a safe exploration of the rover to reach those scientific target position without getting stuck in the risky regions. So in order to do that, let me briefly talk about the second challenge, which is now we are able to map the regolith strengths by walking, but how should we relate this knowledge to the estimation of the rover traversal risk? Because the rovers can come in different type of movement, it can have different payload capacity and different spec. So sometimes the mapping, or oftentimes the mapping from the regolith strength to the traversal risk is not linear. You can be okay and low risk for a long time, but then there's a critical failure point that things quickly go south. So one of the critical things that we want to understand is how do we have these understandings that relate the regolith property to traversal risk. So in order to do that, one of the first questions we need to ask is, why do robots and rovers fail on sand? What is the failure mechanism? And that will enable us to predict the failure point that lead to those locomotion performance degrade. So we do know that sand is an interesting material that behave either solid-like or fluid-like when you interact with them. You can build a sand castle where you elicit the solid-like material of the sand, or you can have the sand flowing through your finger, which behaves like a fluid. So this transition between solid-like and fluid-like behavior is oftentimes the key that lead to either successful or failed locomotion performance in our robots. And the key challenge here is we actually don't have analytical equations at the level of Navier-Stokes equation to relate these microscopic particle dynamics with bulk responses that is going to quickly impact our robot mobility. So to get a better understanding of the relation between the locomotion and the sand behavior, we go back to our fluidized bed and we try to understand what happens when the sand gets weaker when the robot walks on top of them. So we have already showed that when we can use airflow to control precisely the sand stiffness. As we increase airflow, the rate of the force increased by depth or the sand stiffness will decrease from the blue to the red curve. So now if we put a locomotor, either a robot or animal, into this fluidized bed with different airflow, let's see what's going to happen. So you can see that on the top video, there is a gecko moving through relatively packed sand. And in the bottom video is the same gecko moving through much softer sand with larger airflow or lower volume fraction. You can see that from the top video, the gecko is walking on almost solidified sand. In the bottom video, you can see that it's almost swimming in a fluid-like environment. The other thing that we would notice that, of course, the speed drops significantly, and also the sinkage is significantly larger from the top to the bottom. And we run this locomotion experiment with a lot of different animals, including geckos, crabs, and also lizards. And then we also run it with different robots with different appendage shape and width. We all see the same principle. So one key thing that we figure out is that the locomotion success is tightly related to the yield stress behavior of the sand. So for sand or any other yield stress material, their mechanical response is if you apply, they have a threshold yield force or yield stress. When you apply a force or stress that's below that yield stress, they will solidify. They will behave solid-like, and they will not yield. For example, if I put a piece of paper on top of sand, the sand is not going to yield or deform. However, if you apply a force that's larger than the yield stress or yield force, then the sand will yield and behave like fluid. It will deform and yield. How does that relate to the performance of our robots and rovers? Well, every step during locomotion, we are applying a force to the sand. That's usually our mass, right, mg, and if we're running fast, it's mg plus ma, plus our inertial forces. And when sand is relatively rigid, if you look at the top blue force, the blue yield force of the sand, when the applied force intersect with the yield force, that's where the depth where the sand can solidify. So at that particular force, the sand can solidify and support you. You can push against it to move forward. However, as sand weakens, if you look at the green line here, you require much larger depths for sand to solidify. So you will sink to a larger depth before you can effectively move forward. That actually allows us to determine the robot mobility solely based on the sand solidification depths alone. So here we are plotting all the experimental data from 5 different animals and 2 robots. And you can see all the experimental data collapse on a single curve when we plot the speed against the sand solidification depths. And sand solidification depths can exclusively determine the speed, but can also be easily extracted when we match the applied force to the yield force of the material. So this gives us a way to very easily determine the performance. For example, if you predict a very small solidification depth, the robot can move forward quite effectively. However, at a larger solidification depth, the lag keeps fluidizing the sand and swims through and digging a hole in the same place and cannot effectively propel itself forward. So this gives us a very simple model to predict the robot mobility and traversal risk based on the yield strength of material that can be sensed by the robotic lab. So here's how we do it validated in the lab experiment. We use the same lag that already validated that can accurately sense the surface property to poke into different sand stiffness. And then for each sand stiffness plotted on the right, we can use our locomotion model to predict the rover or robot speed depending on its physical spec. And then in order to validate the model effectiveness, we run a robot across the fluidized bed after the sand has been set to a certain strength, and we experimentally measure the robot speed. And the markers indicate the experimentally measured speed, and we compare with the dashed line. You can see that the model quite effectively captures the robot failing trend, and also where the robot start to have trouble in terms of the sand stiffness. So with this lab validation, we then predict, instead of this prototype robot, we make this prediction on larger rovers, and we validate our model in our 2 field analog machines. This is part of our Lustre project led by Cindy Song. at UPenn. And the goal of this project is to see if we can have leg robot with rover to work in collaboration pairs to enable safe traversal and also to recover from failure. So the two field missions that we did for this project, one is at the NASA Ames Center. They have a lunar regolith testbed filled with regolith simulant that has the same property or similar property with the lunar regolith. And what we validated there is the robot's capability to do real-time regolith strength map construction, as well as to use the sense data for traversal risk estimation. The other field mission that we did is back at YSense, where we brought leg robots as well as the rover to validate the capability of both the real-time regolith map construction as well as the rover safe traversal based on the terrain information. So let me show you the first analog mission results. So the experiment setup is we're doing our experiment at this lunar text bed. It's filled with the LHS-1 simulant, which is Lunar Highland simulant. And the test bed is multiple meters long and wide with 15 centimeters of material embedded. We brought in a Scout robot, which is the same spirit-like quadrupedal robot, as well as a bunch of different rovers with different payload capacity. And the goal is to understand if the robot can sensibly pick up the strength mapping by walking around this test bed to inform the rover planning. So to prepare the material to an interesting gradient, we had a design pattern where the darkest cells here represents the tamped region, where for those cells, we tamp the ground to make a high strength or high volume fraction. In the light blue, we rake the surface to make an intermediate strength. And for the lightest cells, shown in the diagram, we sift the sand through to make a super soft and fluffy test material. So we make the entire 7 meter by 4 meter cells through painful preparation manually while wearing the bunny suit because there's fine dust in the lunar regolith simulant into the graded pattern that we wanted. And we also measure the ground truth of that. And then after we set the ground, we send the leg Scout through, and you might notice that it's wearing the child's pants just for dust proof. So we found that nothing works better than wearing 2 6-year-old pants on the robot for sandproof. So the robot walks around and makes the regolith sensing through every step. And then we can plot these terrain strength map from the data. So on the left side, the panel A is showing an overlay of the designed pattern on the regolith testbed, and C and D is showing the design pattern and the robot actual measurements. So the black dots on the panel D is showing the robot footprint. So it's doing a zigzagging pattern with the 4 different lines. The color here is showing the robot inferred strength of the stiffness. So the red region indicates high strength, blue region indicates lowest strength, and purple indicates intermediate. You can see that it matches really well with the middle pattern, which is the designed pattern of the ground truth. The transparency on the panel D from the robot scouting indicates the certainty. So the high transparency region indicates that we don't have sufficient data there, so we don't have enough confidence of the measurements, but we can still have estimation from the Gaussian process. So based on the terrain map, we then compute the traversal risk based on the rover's spec and also sensor payload. From the bottom to the top, we are estimating for different sensor payload capacity. So you can see that at the bottom where the rover is carrying 40 kilo of payload, the traversal risk is relatively low. But as you increase the payload capacity from 40 to 160 kilo, the risk region, high risk region extends significantly, and the low risk path becomes a corridor. So we can use this to guide the payload configuration across different rovers. We can also plug in different rover parameter to generate the same traversal risk map. To validate this traversal risk map, we deployed our leg robots and also the rover in our Y-sense field site. So the left side, I'm showing you a LiDAR scan of our field site, which give us a rough traversal path direction for the rover to go through. And the wide region is where we potentially want to send the rover. So before that, we send the leg robot to do the scouting and figure out where the sand is soft versus rigid. This is, we just did this field work last month, so I'm showing you a live screening recording from our interface. So what I'm showing here is as the robot is zigzagging through the scouting region, the bottom is, again, a live screen recording from our live map construction panel, where the colored region and the green dot is showing the robot footprints recorded by the differential GPS, and the colors are the live construction of the strength map, where the red shows high strength and the blue shows low strength. There are also a lot of the graph showing there, where the first panel is showing the full signal from the two front legs constantly at all times. The second panel is showing the penetration region, which we use to estimate the ground condition. And the third and the fourth is showing the mean and standard deviation of surface condition. So using this completed regolith strength map, we use our model to convert to the traversal risk, which is showing on the right side there, which we can do the rover path planning based upon it. So the two paths that we compared at Y-sense, one is the naive path, which the robot directly goes through the region from start to the goal, and versus the second path is the risk-aware path, where the robot uses the risk map to avoid the red region, which is the high-risk region. So let me show you the video of the first naive path, where the rover was commanded to strictly go towards the goal. Initially, it's the low-risk region the rover is traversing through, so you can see the rover speed is relatively high. As it approaches the yellow to the red region, you can see the speed start to decrease. And eventually, if you pay attention to the right back wheel, you are going to see that when it enters the red region, the wheel start to spin in place and the rover will get stuck. And then, as opposed to that, in this risk-aware path of the bottom video, oops, see if that plays. That's unfortunate, so you have to take my word for it. In the risk-aware path, where we drive the robot following the risk-aware path, the rover did not encounter the same stuck pattern, and it strictly goes through, circumvent the soft sand pit, and successfully reach the goal location towards the next view. One thing that you might notice that is in this naive path, there is a dog robot here holding a telescoping arm standing by, and you might wonder what that is. And this is actually the second part of our Luster project, mostly done by Cindy and Mark's group, where we wonder if the rover does get stuck, if unexpected failure does occur, can we use the Scout robot to land arm to help them get out of trouble? And this is one of our initial tests, the first time we test this proposed scheme. So we have two dogs, and they each have a telescoping arm. They can automatically dock with the rover. And in this case, the rover is trying to climb up a steep sand incline, and it's on the edge of getting stuck. You will see a couple times during this traverse the rover getting stuck and the wheel spin in place. However, we have two Scout robots. Then they notice the rover is in trouble. They will go and dock with the rover. The telescoping arm can also extract or extend in length, so the robot can also stay in a soft region, anchor themselves, and then use the chassis arm to push or pull on the rover to get them out of trouble. So in this case, it's our first attempt to show that using the Scout robot, we can actually help with the failure recovery in case any unexpected failure occurred. So with that, we're hoping that going forward, the scouting robot can provide a useful terrain property estimation, but also provide useful guide on failure recovery if the rover gets in trouble to enhance our science and prevent the catastrophic failures that we might encounter during the planetary exploration. So thank you very much, and I'm happy to answer any questions that you may have. Thank you.
I'm curious how much work it takes to calibrate this kind of proprioceptive sensing in the first place, and how easy it gets decalibrated, and what measures you take against that.
Yes. So there are different levels of calibration. So we calibrate first in the joint level. So we want to understand whether torque estimation from a single motor is accurate. Can we use, for example, the nominated torque constant, or do we need to actually do any calibration? So we first do that for every single joint we have. And we do realize that it's actually pretty, using the nominated torque constant that comes with the manufacturer, we can directly use those, and it actually works pretty well. Then when we put it into any configuration, so I showed you the leg, but we also have like turtle robot, we have a variety of different robots bio-inspired. So in every single configuration, we also then do like appendage level for sensor calibration. So one thing that I showed you is during the vertical penetration, we both do the penetration ground truth. We also hang weight on the leg in different configuration, trying to make sure that whether it can calibrate well. And then, of course, when the robot start to walk and run, that's a different level of calibration, because any of the inertia of the robot or the body pitch, roll, or yaw, and also the accuracy in detecting the ground contact will cause additional noises and the inaccuracy in the force sensing. So that's actually still in some of our ongoing work, where one of the work we're comparing different gait speed. So when your robot is walking super dynamically and fast versus walk slowly and more statically, how much of that inertia is influencing the force sensing accuracy. What we have discovered, we just submitted our paper to ENGR last week, or 2 weeks ago, is that we found when we increase the gate speed, the strength of the sand can still be picked up relatively reasonably. However, the detecting the layering and the texture, for example, the surface crust, become more and more unreliable when you start to move more dynamically. So that's where we're at right now.
And do you have any drift issues at all, or?
The time scale for that is relatively long, so the sand can stuck in. Well, our robot is very beaten. It has been brought to the sandy area, the lunar dust to kind of simulant, and also the icy regolith that melts, and the water and the sand might get into the joint, which we broke the warren like a million times already, right? So our robot's pretty old. It's an old dog now, so some of the joints are worse than others. So over time, there will be performance degree that we do need to characterize the joint torque and also the cogging. The friction definitely gets worse over time. But that's happening at a slightly longer period, yeah. Unless we overheat our motors.
Thank you so much.
Thank you for the talk. It was very interesting. This question is related, but maybe a little bit outside the scope. But I'm curious, in this sort of system, you have a small rover and then other, essentially robots to assist it. What does the optimization look like? Because any material sent, you can spend in different ways. And you could spend that on smaller robots that can assist the larger rover, to navigate more effectively. Or you could spend that material on just hardening the larger rover to, be more effective in navigating the terrain. So how do you think about optimizing that? It's, you could have a second robot or just wider tracks on the rover. What's that thought process like?
Yes, that's a great question. That's what we think about every day. And that's essentially why we come up with this trusses project, right? So there are times where individual robots have limited capability that we want to unite together to collectively make a more challenging task done. But other times we also want to have more units. One is if one fails, we have others just keep going. And 2 is that we can be much more efficient, covering a larger ground within the same unit time that we have during the mission. So the kind of one of the idea of this project is, can we have this kind of team of robot that individually they already have pretty good capability, and maybe each of them can carry different sensor payload. But the idea is that they are also feel the environment every step, so they can talk to each other, say, hey, I'm in a patch where I think, you robot who's carrying this green size camera should come over to look at the spot, because that's really, I think, the governing hypothesis here that's governing the environment here. Or the other robot can call on other robot to say, hey, you should really look at the spectral measurement here in the spot that I'm at. And then at the times where collective locomotion, or maybe one robot can anchor to the slope and then push the other robot to send it to over a certain dune or a lunar crater, we want the robot to have the capability to form a larger, more capable unit to help each other to achieve these more advanced complex tasks. So yeah, great question. We haven't fully figured out the full scheme yet, but I think that's definitely a very interesting direction to explore.
Thank you so much for the talk. It's really interesting. I'm just curious whether that's wind could have an effect on maybe changing the forces or making it so that the results aren't as easy to read or use in the system.
So let me just make sure I understand the question. So you mean if there are environmental conditions, for example, the wind blowing or the humidity or other conditions happening, thermal temperature change, does that influence the results? Is that correct? Okay. So I love that question because that sort of speaks to why we need to have high temporal spatial density data. So at Mount Hood, which is our the icy regolith material site, it's actually a time varying system if you think about it. So it has ice that can actively melt and refreeze, right, as the robot walks by. And we actually take thermal images during the sunrise and the sunset and also throughout the day to look at the temperature changes. And then we relay them to the force changes. So this is actually something we're currently very excited about, is looking at how the force can relate to the environmental condition change and then trying to figure out the dominant factors, what's causing the change in the surface property, because it's such low cost now. You can have the robot take one pass in the day, you can have it go back and do a repeated trial and see, okay, what changes, right? So if there's anything, let's say during the lunar temperature cycle or some of the other conditions change you expect to actually influence the surface property, we can do that over multiple traverses and to figure that out. But yeah, it'll be very interesting to explore. Does that answer your question?
Yeah.
Okay.
Thank you so much for the talk. I saw on one of your slides you put hands on the robot. So my question is, where's the mechanical design of the robot going to combat these sort of sand, dust, water? Are you thinking of wrapping the robot or just increasing the robustness of them?
Yeah, that's a great question. As we going towards more flight-oriented mission, it's definitely going to be a very critical challenge because you don't want to seal everything up because the motors can overheat, especially in atmosphere like the many of the destinations that we want to go to. The thermal challenge is very real. We actually just did our last field trip at Y-Sands in August, in the middle of the desert in summer. Terrible idea. Don't go there. I don't know what we're thinking. That's the only time that the whole team, we have 40 people going, so that's the only time that everyone is available. But we had to wake up at 4 a.m. each day and then finish our work at around 10 or 11 at latest before it gets dangerous for human to work in there. And the motor, we saw it's going to be the cutoff for human health and safety, but the robots and even the laptops and batteries, they give out super fast, right, as the temperature rises. So that's a balance that we need to think very carefully about, is how much of the sand-proof and waterproof that we need to do as compared to the heat dissipation. So yeah, that's something we haven't fully figured out yet, but we're looking forward to looking at those design choices and design challenges. Great question. Thank you. Yeah.
Thank you so much for the talk. I was wondering what sort of considerations you would maybe make if you wanted to maybe extend the lifetime of the robot, maybe on the path planning side, or finding areas of high interest and reducing the amount that the robot would maybe have to travel?
Yeah. This is such a great question. I didn't have time to go into this whole other aspect of the planning and decision-making side of our study. So one of our critical components of our project is looking at the decision-making, right, operation planning. So a key question is how to balance the reward and risk, and then of course, within the time and the battery budget that you have. So a lot of our work is looking at how currently we have like a back room, right? We have scientists on Earth looking at the rover data that pass back, and then we decide where to send the rover next. As time goes by, if we have a robot like this, you can't ask the dog to just like hold one leg or like, all right, where do you want me to step next? And how do you want me to make that step? Because they can step vertically, it can scrape, it can do a variety of different gaits. It's all going to matter how we collect data and what locomotion risk we have. So it's really critical for us to make our robots smarter, right? It can make these complex decisions based on the incoming environments and based on the change condition of the environment. So a lot of our work is focused on, in collaboration with decision scientists, to look at how humans make these decisions, how we adapt our experiment plan and data collection plan based on all the information that we gather. So we designed this both the web-based interface and also field control interface to explicitly looking at humans' decision making, make that very explicit, such that we can convert that into algorithm for the robot to also reason about these things and then make decisions and adapt their decisions under to balance the reward and risk. So yeah, I'm happy to talk more about some of those details with you if you're interested. Yeah.
If you guys have investigated any other failure cases, such as like slippage on snow,
I'm so glad you asked.
or for example, sand that is too soft. Or
Yeah, remember this video I showed you where I cut off just in time, right? So I'm going to show you the one that I did not cut off. Give me 1 second. Let's pull that out real quick. All right, here's the same video, but it's going to show you 2 more seconds of that video. So we do have slippage, but this one, pay attention to the left front leg. It's fine until it's really not fine, right? So what happened there, right? So, it's not just sinkage, because sinkage, I have seen a lot. I work on locomotion on sand a lot. If it's just sinkage, the robot will step really deep, but it's not going to have a critical failure. And the challenge here is that if you look at the right side plot, it's the IC regolith during that step, right? What's happening, the force. You see this like giant stick slip force failure. So essentially you are stepping in, make an ice sheet, break it, fresh snow again, make another ice sheet, break it. It was terrible, right? And also ice and snow are cohesive. So unlike sand, when you pinch it in, you have a large sinkage, no biggie, right? So you lift your leg, there's almost no force when you extract your leg. But in cohesive media like ice and snow, you are basically ice picking your leg into a narrow hole. Except you trace all the way through, you have a passive compliance, so there must be some smart design we can do. But if you are not doing that, it becomes you are locked into a singularity, right? And it happens so fast, because if you look at these stick slips, there's no way you prepare for that, right? So once you pass that yield strength, you are basically in for good. So you basically pinch your leg all the way in. And that's not even the only failure mode, right? So, let me move this one in here. You ask about slippage. So, if you, can I play that, please? Yeah. So, you have a lot of different, control strategy you can use if you are balancing the sinkage well. But then if for example, depending on your pinching angle, right? So if you pinch more deep, vertically down, you'll have the sinkage failure and the stuck failure. If you pinch more horizontal, you'll have the slippage failure. So there's a lot of very interesting failure modes that I'm actually very excited when we are seeing these in the field. That's like the best moment ever, because you can see that where these environment conditions and really this like interesting rich force signature are coupling into the locomotion failures that you saw. So we are running all kinds of, we're making ice in the lab, we're mixing ice with soil, and we're changing the foot design, we're changing, we're looking at the hypothesis about how touchdown angle, how touchdown speed, how trajectory of the leg is going to influence the elicit response of the IC regolith and among other materials. So that's a huge part of my group's work, is looking at how do you strategically interact with your environment such that you can improve on your mobility or other tasks that you want to do. So thank you for that question.
I have maybe one more. Given that your feet are now partly sensors,
Yes.
is there a special foot geometry that would be more optimal for sensing?
That's a wonderful question. That's what we're looking at right now. So let me think about how to explain this. So we can make different, first of all, we can make different trajectory. And right now I'm showing you the most simple thing is penetrate right in, right? And then look at the slope. But what if for locomotion, I need to make a different arbitrary trajectory? What information do I gather? So what we are doing is we are using a representation called resistive force theory. So that essentially breaks down the arbitrary either leg shape or leg trajectory into infinitesimal pieces. So each piece is a flat plate. It has a different orientation and different moving direction. So each time step, whatever trajectory, random trajectory or random shape I have, I'm gathering the force responses still as flat plates, but I sum them together. So we can solve for that. But there's a trade-off, which is if you design your feet in a way or if you move your trajectory in a way, some of them more informative than others to sample in that parameter space to allow you to figure out the terrain property. But also more interestingly is depending on your hypothesis, right? So if my hypothesis is to distinguish dry sand from cohesive material, if my goal is to look at the rupture failure of the sand, I will need to focus on different part of my parameter space. That requires different design, that requires different trajectory. So that's something that we are currently doing as of this moment. So thank you for you predicted you predicted our move essentially. So yeah, that's a very exciting thing to think about is all these trade-off now that the locomotive appendage is your sensor. How to design it for the trade-off, how to control it for the trade-off, and all these questions, how to select your hardware itself for the trade-off is all the questions that we are hoping to answer right now. Yeah, sure.
For the very interesting presentation. And so today, you're focused on the leg the sensing. And so do you have any ideas to use this real-time sensing for the manipulation for the robot? And so real-time operation and optimizations.
Yeah, so yeah, I think for real robot, how to apply this. Yeah, I was surprised that no one asked me that. Usually I get this question right away. So yes, so actually for the traversal risk, we are actually based on wheeled versus leg coming up with a different mapping of the regolith strength to the traversal risk. So the idea is similar to what I was mentioning, this resistive force theory by breaking either the wheel contacting surface or the leg contacting surface into infinitesimal arrays of flat plate. So this way, whatever arbitrary geometry you have or trajectory, right? The motion, for example, the wheel is more kind of a shear motion and the leg might be like stepping down along with the pushing. You can basically just use the same method to break them down into this general representation and looking at each infinitesimal plate and how their force is going to either give you propulsion or not sufficient propulsion that will result in large slippage. So it's the same methodology we plan to apply to both to adapt to general platform-specific risk. Yeah.
Well, thank you very much. And once again, thank you. And we can wander over to the SRC for any follow-up questions.
Okay.